Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are wrapping up Chapter 4 on the study of entropy in this video lesson, and we are going to be looking at how we can use reversible process calculations to determine answers for real processes by using process efficiencies. We use process efficiencies to calculate the actual work from a process. Now, we're going to define the process efficiency as eta. We've used that when we started talking about like an engine or something like that. Thermal efficiency, this is almost but not quite the same. This is a ratio of the actual performance of a device to the ideal performance. And we're always going to do this ratio so that the value we get is going to always be trapped between 0 and 1. Okay? Now we're going to need some subscripts to make this make sense. And so when we see a subscript A, that's going to mean it's the actual real process, not reversible. S means the process is reversible and adiabatic, or an isentropic process. And T will stand for the ideal process being isothermal. We have a lot of common processes, so let's look at those one at a time. First, let's consider a turbine. The purpose of a turbine is to produce power. Okay? So therefore, we want to compare the actual to the ideal power. The reality is friction is going to cause some loss, so we're not going to get quite as much work produced as what we had hoped for. Therefore, we can define the efficiency for a turbine to be the actual work to the ideal, and the ideal in this case is going to be reversible and adiabatic. No energy is lost as heat. Or we can say, based on a first law balance for no changes in kinetic and potential energy, that this is the ratio of the difference between the inlet enthalpy and the actual exit enthalpy compared to the inlet enthalpy and the ideal exit enthalpy. So we're starting with the same feed material. We're going to imagine that we ran this turbine reversibly, and then we'll use that and compare to what we get in reality. So A is the real exit state. S is the ideal reversible and adiabatic exit state. Now, pumps or compressors, the reality is that we have to, we plug a pump or a compressor into the wall to make them work, and we have to pay for that. The reality is it's going to require more power to run these things than what we would like due to, again, frictional losses. And so therefore, I'm going to have a very similar ratio to the pump, but it's going to be upside down. The smaller value is going to be the ideal, okay? The reality is going to be a larger value of power. And my ideal could be either that it's insulated, in which case reversible and adiabatic, or that it is isothermal. If I run a cooling system through there, especially with gas compressors, we're likely to do this, then my ideal would be reversible and isothermal. That's going to result in these expressions. Typically, pumps are adiabatic, so the efficiency of a pump would be Ws over Wa. And the efficiency for a compressor, which is typically operated isothermally, would be W sub T over W sub A. So we're maintaining the exit temperature as the same as the inlet temperature in those cases. Our last common process is going to be the nozzle. Now, in a nozzle, the goal is a change in kinetic energy. And of course, friction is going to impact this. We had an example earlier, and I said that reversible calculation gave us the maximum possible velocity we could have. So the ideal is going to be usually reversible and adiabatic. They're very small devices, so we don't expect much opportunity to lose heat, okay, through the walls of a nozzle. So therefore, the actual kinetic energy divided by the ideal kinetic energy. And in this case, it's 1/2 the actual exit velocity squared over 1/2 the ideal exit velocity squared. And of course, those 1/2s can cancel, the squares cannot, so we end up with the ratio of the actual velocity to the ideal velocity squared is going to be the nozzle efficiency. Let's look at how we might use this by looking at an example with a turbine. So air, and we're going to consider it to be an ideal gas with C sub P and C sub V given, will be expanded in an adiabatic steady flow turbine. So therefore our ideal will be reversible and adiabatic, therefore constant entropy. It's starting as 100 or 1000 kilopascals, 280 degrees C, and it's going to exit at 200 kilopascals. We want to know what's the actual exit state for an 85% efficient turbine, and then what is the entropy change for the process. This is an example where we have an ideal gas that's reversible and adiabatic is going to be how we begin our calculations. And if that's the case, then that is polytropic with the exponent equal to gamma, right? So PV to the gamma power is going to be a constant, okay? Gamma is C sub P over C sub V, which in this case is 1.4. I can use this because I can estimate what the ideal exit temperature will be, right? We've done these calculations earlier. So using the formulas for these reversible and adiabatic ideal gases, 553 is my temperature. Remember, you always need to work with kelvins. The one exception would be when you're doing delta T. Those pressures are absolute 200 kilopascals over 1000 to the 0.4 over 1.4 power. And running this through the calculator, we get 349 Kelvin. And just so you know, it's 76 degrees C. Okay, so it's going to be much cooler at the exit. All right. Now, what we know is that the efficiency is 0.85. That is the actual work divided by the ideal work, which is delta H for the actual over delta H for the ideal. In this case, if C sub P is constant, this is just C sub P times Ti minus Te actual over C sub P times Ti minus Te ideal. C sub P is the same in each case. Ti is the same in each case. So 553 minus Te actual over 553 minus 349. And I get that the actual exit temperature is 379.8 Kelvin, 380 Kelvin, okay, or 106.8 degrees C. So not quite as much of a temperature drop, but it did still drop temperature. What about that entropy change? Well, again, if it's constant C sub P, delta S is C sub P times the natural log of T2 over T1 minus R ln of P2 over P1. I selected this equation because I have pressure information and I don't have volume. If I use C sub V, I need volumes. So in this case, 1.005 kilojoules per kilogram Kelvin times the natural log of my ratio of my T's, 380 over 553, minus R, the difference between those, 0.287 kilojoules per kilogram K. So both of these will have the same units, times the natural log of 200 over 1,000. And so delta S is 0.0843 kilojoules per kilogram K. This completes Chapter 4. We're next going to be looking at Chapter 5, so we're going to be going very much into applications. What is all of this good for? Thank you very much for your time.